Find the nominal moment in the beam in pounds-inches. In this problem, a beam having a rectangular cross-section is reinforced with number 9 sized rebar. The compressive strength in the concrete is provided, as well as the yield stress and the Young's modulus of the steel. The equation for a moment is a force times a distance. For a rectangular shaped beam, the moment equals 0.85 times the compressive strength of the concrete times a length A times the width of the beam B times the quantity depth to steel D minus the length A divided by 2. The problem statement provides the values for compressive strength, beam width, and depth to steel. So we're left to determine the length, A. From the equation for axial force equilibrium, where the compressive force in the concrete is equated to the tensile force developed in the steel, we can isolate the variable A, which equals the area of steel in the beam, AS, times the stress developed in the steel, Fs, divided by the quantity 0.85 times F prime C times B. For this beam, the area of steel equals 6 inches squared, which is 6 number 9 bars of steel times 1 inch squared for every number 9 bar of steel. Since we already know the compressive strength of the concrete, F prime C, and the beam width, B, the remaining variable to compute is the stress in the steel, Fs. At this point in the analysis, it is typical to assume that the steel yields, and that the stress in the steel equals the yield stress of the steel. We'll check to assure that this assumption is valid later in the problem. After plugging in all the variables, we compute A equals 10.08 inches. Now we'll check our assumption that the steel yields. If the strain in the steel is at least the yield strain of the steel, our assumption is true and A equals 10.08 inches. If the strain in the steel is less than the yield strain in the steel, our assumption is false and A needs to be recalculated. The yield strain in the steel equals the yield stress in the steel, Fy, divided by the Young's modulus of the steel, Es. Since both of these values are provided, we compute the yield strain in the steel to equal 2.07 times 10 to the negative 3. From strain compatibility, the strain in the steel, epsilon s, equals 0.003 times the quantity d minus c divided by c, where d equals the depth of the steel, 15 inches, and c equals a divided by beta, where our assumed value of a equals 10.08 inches, and beta ranges between 0.65 and 0.85, based on the compressive strength of the concrete. Since the concrete compressive strength is 3,500 pounds per square inch, this value falls in the region where beta equals 0.85. Plugging this value in for beta and 10.08 inches in for A, the value of C equals 11.86 inches. Substituting in this value, as well as the depth, D, the strain in the steel equals 7.94 times 10 to the negative 4. When comparing strain in the steel to the yield strain in the steel, we determine that our assumption is false. The stress in the steel does not equal the yield stress, and we need to recalculate the value of A. So we return to our equation for A. This time, instead of assuming the stress in the steel yields, we'll equate the stress in the steel to the Young's modulus of the steel times the strain in the steel. We already know the Young's modulus in the steel, and we can use strain compatibility to equate the strain in the steel to 0.003 times the quantity D minus C over C. As before, D equals 15 inches. Next, we'll multiply this quantity by beta over beta and revise our equation. Since we know C times beta equals A, we can make this substitution and simplify. Now we can substitute this revised equation for the stress in the steel, Fs, back into our previous equation to solve for the length, A. After a bit of algebra, we end up with a quadratic equation with respect to A. After substituting in the known variables and simplifying the equation, the roots of the quadratic equation compute to negative 22.80 inches and 8.18 inches. Therefore, our value of A equals 8.18 inches. Now we can return to our original equation for the nominal moment in the beam. Plug in the previous values we already knew, then plug in the value of A, 8.18 inches, and the nominal moment in the beam equals 3.186 times 10 to the 6 pounds-inches. When reviewing the possible solutions, the answer is C.